Teleportation will commence in 5 minutes. Do not leave any luggage unattended. Unattended luggage will be removed and destroyed. Attention, ladies and gentlemen. This is an announcement from planet X31. Please take your seats.
first Nobel Prize winner to participate in science and academics. For that, we should all give him a big applause. Try to convince you that we live in extra dimensions, that there exist parallel realities, multiple universes, and we just happen to live in one of these universes. He will try to convince you that every single thing in the world originates from one single identity called a string. And when it vibrates, it gives rise to all this plethora of phenomena that we observe every day.
Ladies and gentlemen, after the words of David Gross, the jazz trio Andromeda is performing live. On acoustic instruments, they're exploring the relationship between composition and improvisation, human and the universe. All compositions are inspired by different phenomena in the cosmos.
Transmission.
Well, that was one of the more interesting introductions been given. I give lectures many places around the world to audiences who are interested in science, and this is certainly one of the more interesting venues, which I hope to do justice to. I really would like, so I have a talk, a PowerPoint presentation, which is pretty good. But I do like to interact with the audience, and so I'll be looking at you all to try to see how you follow it. My talk tends to go on quite a bit depending on the audience. But I'm also perfectly happy for you to interrupt me with questions. That might make it even more interesting. So, I am going to tell you about string theory, but to set the stage, I'm going to tell you I'm going to tell you about what we really know for sure, the state of elementary particle physics, and the very exciting discoveries that are being made and we hope will shortly be made at the Large Hadron Collider, the famous LHC, which I'm sure you've all heard about in the last few years. And then based on a little tutorial on what we do know, for sure, we will go on to what we don't know, which is even more interesting, and to string theory, and more generally, quantum gravity and cosmology. Now, I like to actually collect cartoons about string theory and about science. They give me a feeling for how fundamental physics is viewed by the public at large and by the intelligentsia. And here is a cartoon I saw maybe 25 years ago in the New Yorker magazine, which has wonderful cartoons, and it's the first thing I read when I open the New Yorker. And there I found this lovely cartoon in which two intellectuals are walking down the street in New York. You can tell they're intellectuals by American standards because she has long hair and glasses and he has no hair and glasses. And she says to him, "It's all string theory to me." This was years ago, and I thought this was fantastic that string theory had replaced Greek. But some years later, in the same magazine, there appeared this cartoon, Harvey's Place, tonight 5 to 8, is string theory bullshit. Well, you know, fads go up and down, and there were some really bad, stupid books about string theory and why it was all wrong. So this was a bit depressing, but a year or two later, a colleague sent me this advertisement, which appeared in the New York Times weekly magazine. String theory, when physics gets physical. Restoring my faith in the American mass media. Well, let me tell you a bit about what we do know. And we actually know an immense amount about the microscopic world where we, people like me, theoretical and experimental physicists who call themselves elementary particle theorists or experimenters or high energy particle physicists. High energy because we need high energy to look at short distances into the micro world. And we do what you might call nanophysics. So there are a lot of my colleagues who study quantum matter. They study atoms and solids and semiconductors down to the level of ordinary atoms, which are about 1/10 of a nanometer. And they're very proud that they're doing nanophysics. And in fact, if you're doing nanophysics, you can easily get support from governments who think that he who knows nanophysics rules the world. We actually study nanophysics, but our applications of what we do will either be never or a long time in the future. So it's still, however, governments are willing to pay, so far, billions and billions of euros and dollars to explore the structure of matter down to billions of a billionth of a meter. And in the last only 100 years, we have managed to explore the atom and the nucleus and the particles that make up the atom and the nucleus down to this incredibly short distances. And it all began just 100 years ago with Rutherford, who, in order to try to figure out what an atom was, and it was still somewhat speculative whether atoms even existed, scattered alpha particles, which themselves are the nucleus of helium atoms, off a gold foil, and he, actually his students, sat around in the dark for hours, and then they observed the scintillations that the scattered alpha particles made when they were deflected by the gold. And by measuring the deflection, how many atoms were scattered this way, that way, and how many backwards and back at you, Rutherford deduced that the atom actually was not some kind of mushy liquid or solid object, but rather mostly vacuum. In the center, there was a very little small region where all the mass, almost all the mass, was located, and all the positive charge, which he called the nucleus, and the electrons somehow were spinning or moving around the nucleus, much like the planets around the sun. That was his model of the atom, and that discovery, only 102 years ago, it's a short time in human history. The people who live 100 years led us to the understanding of atoms, to the discovery of quantum mechanics, and to the establishment of this method of studying what goes on at short distances. You want to figure out what goes on at short distances, you scatter one kind of particle off another, at higher and higher energies and look at what comes out of the collision. And that's what we do today as well, except we do it with energies that are a million times greater, with vast particle accelerators. And using that, we deduced, or physics and chemistry, some physicists deduced over the last 100 years the structure of matter within the atom. And especially, the hard part was to figure out what goes on inside this teeny nucleus that Rutherford discovered. And what do we mean by understand? Well, there are two things we have to understand. One, what makes up, what kind of particles, what kind of matter is in the atom. And second of all, how does it work? What are the laws that govern the motion of these particles? So we discovered that there were electrons and nuclei. And over the last 50 or so years, we discovered the nature of these nuclei, that the nucleus of atoms, which here is blown up by 100,000 times, is actually made up of neutrons and protons, which in turn out to be made up of quarks. And quarks and electrons, in similar patterns of quarks, heavier quarks and electrons, are essentially, until recently, the only elementary particles, elementary point-like constituents of matter that we have discovered, that make up all the matter we observe in the universe. More or less. And the other part of the story is not just what are the elementary particles, what are the elementary atoms of matter, but also what are the laws that act on matter. And, there is the law of electricity and magnetism that acts on charged particles, electrically charged particles, and that's what holds the atom together. To truly understand how that works inside the atom, Niels Bohr of Copenhagen and his friends had to invent quantum mechanics, which happened very shortly after Rutherford's discovery of the nucleus. What happens inside the nucleus itself is due to two other forces which were quite mysterious and not known before. The nuclear forces. One is the strong nuclear force that holds the quarks together, and two is the weak nuclear force which turns one kind of quark into another. And I'll discuss those briefly, but these three forces are enough, together with these kinds of elementary particles, to explain all of atomic matter, molecular atoms and molecules, and thereby all of chemistry and biochemistry and us and everything we see around us. And these nuclear forces explain everything going on in the nucleus. And that's an amazing theory, which we call the Standard Model. Now, the Standard Model, I've written down these equations, which you all know very well. And, but this is it. I can put this on one T-shirt, and you can solve, more or less in principle, we believe, and a lot of in practice, calculate just about any experiment that has ever been done or that we're doing nowadays, all is in accord with this so-called model, which is really much more than a model. It's so unbelievably successful in this reductionist sense, and that we should really call it a standard theory. It is a very powerful theory, and it is sort of the culmination of 2,000 years of a journey starting with Democritus, who said everything's made out of atoms. It just looks like there's flowers and pieces of wood and glass, but it's all just atoms of carbon and silicon and oxygen and atoms. And now we understand that that's true and what the atoms are made out of, and just about all their properties can be calculated from this incredibly successful theory, which has been tested over and over again. And my experimental friends continue at the LHC, for example, and many other experiments to subject this theory to precise tests with the hope of overthrowing it. That's what experimenters want to do. They want to show that theorists are all wrong. Now, theorists want to experimenters to show, some of them want the experimenters to show that they're right. And some of them want the experimenters to show that other theorists are wrong. But so when these experiments continue to test the validity of this standard theory and find that it works, some of us are kind of happy, but also a bit disappointed, because it's when things don't work that we learn something new. But also, when things do work, we learn that, well, this is a good starting point at least, and it is an unbelievably successful theory. What is it? The standard, so-called standard theory model is, as I said, based on two aspects. We have matter. Matter comes in three families which are more or less have the same properties, except that the basic particles, these quarks and so-called leptons, electron and neutrino, each family has different masses. They weigh. These are the lightest ones, these are heavier, these are even heavier. We're made out of up and down quarks, which together form the proton and neutron, which make up our nuclei, and then electrons form atoms together with those nuclei. Neutrinos, which are almost massless, but not quite, are paired with these electrons. And then there are two families which no one ordered, and we don't understand why they're there, but they are. And they have been observed and their properties measured, but we can't either predict them or calculate their properties, their masses. What we can calculate with extraordinary precision, and is in a sense more fundamental, are the forces that act on these three families of quarks and leptons. These are, as I said before, the force of electromagnetism, which acts on any particle that has a charge. And, like charges attract, opposite charges repel, the inverse square law, is true and known from classical E&M. And it determines the structure of atoms. Electrons are charged, and they interact with the nuclei, which also are electrically charged. And it's the quantum mechanical theory of charged particles like that gives rise to the structure of atoms and of molecules. But then, as I remarked before, we have these other forces, the force that holds the quarks together. Quarks have another kind of charge, we call it color, and they're held together by a strong force. The carrier of the electric force we call a field, the electromagnetic field. The field also manifests itself as waves in that field. Those are light waves, as Maxwell discovered. In the quantum theory, those waves also look like particles sometimes. Those quanta of light are called photons. In the case of the strong force, there are also a chromodynamic field that carries the force, and the gluons are the so-called quanta of that field. And then there's another final force that acts both on quarks and on electrons and turns one of these quarks into another and an electron into a neutrino. That's what gives rise to the transmutation of elements, or radioactivity. And finally, the last item in the standard model is another kind of field that was introduced to explain the weak force, called the Higgs field. And as you probably have all heard last year, the discovery of this particle was a big deal. And I'll discuss that a bit. This theory works, as it said there, from nanometer, as far as we can tell, and perhaps down to distances even a million times smaller, as far as we can extrapolate, to the edge of the universe. It is an incredibly successful theory. Normally you don't trust people like me, theoretical physicists, to work with pencil and paper and mathematical formulas to extrapolate a theory developed for one regime by many orders of magnitude. But in this case, it has worked. And so, as I said before, science is this paradoxical thing. When you're successful, you're very happy, but also unhappy because okay, what's left to do? What do we do now? And I often say that the most important product of knowledge is ignorance. Now, that I don't, of course, what?
Ignorance for enlightenment.
Ignorance?
For enlightenment.
Well, ignorance, what I mean by ignorance is not, the bad kind of ignorance that leads to racism or to intolerance or causes many of the problems in the world around us, but rather the kind of ignorance that you have once you understand something new, a new phenomenon, you understand it finally, you then suddenly realize that there are questions you never thought to ask before because you didn't know enough to be intelligently ignorant. For example, questions that are sort of why questions. And I'm going to be focusing in a while on those questions that we're asking now that we simply didn't know enough to ask 30 years ago, 40 years ago. But now that we've constructed this incredible theory that is capable of predicting most of what we observe, we begin to ask totally new and even more ambitious questions because we are now much more knowledgeable and therefore intelligently ignorant. But what I mean by ignorance really are questions that can be answered by the scientific method. A lot of interesting questions like why is there something rather than nothing? You can ask those, people have asked those questions forever, but they're not scientific and I don't find them that interesting because I don't have that much hope that they're going to be answered. I like questions that can be answered by observation or by experiment or by what I do, which is theoretical speculation, theory, which tries to make predictions of what observations or experiment will observe. And those are the interesting questions, and you have to know quite a bit to ask those questions wisely, which is why, unfortunately, to do science, to actually participate in the excitement, you have to go to school and go to graduate school. It takes a while because you have to know enough to be intelligently ignorant. It's sort of like we're pushing out. We live in a sea of ignorance. We're born not knowing very much with some built-in tools, it appears, and we gradually, and as a species, expand out into the sea of ignorance. But we're only really aware of the ignorance on the boundaries. Out here, this part of the sea of ignorance is too far away. We can't see what the questions are, what the issues are. It's very much like exploring a new continent. You're only aware of what it is, of the frontiers of your ignorance. And as we expand out, we ask lots of interesting new questions, and the ones I will focus on will be the ones that you've heard a lot about that are being explored now at the LHC, the Higgs mechanism. And then some of the strange discoveries of astronomers, dark matter, dark energy, which hint at new physics. Then there's the goal of unifying all the forces of nature, which has led many of us to string theory. And then there are the new questions that are posed largely by theorists who are exploring unification and quantum gravity and cosmology, having to do with the nature of space and time itself. What is space? What is time? So, first I want to tell you something about nothing, the vacuum. Now sometimes I tell my non-physicist friends that I spend most of my life studying nothing. And it's true, to a large extent, what in fundamental physics, what we study are the properties of the quantum vacuum. And you might think that's strange because most people's picture of a vacuum is a pretty boring place, but it is the properties of a vacuum that give rise to, for example, this phenomenon of asymptotic freedom or port confinement that explain the strong nuclear force, the symmetry breaking, which gives you the Higgs mechanism, which has been so much in the news. And in general, the fact that the vacuum is so complicated gives rise to the possibility of totally new aspects of physics that are hidden from us by this strange vacuum state. But this is what most people think about if you ask them what the vacuum is. Nothing. Take this room and remove everybody and all the chairs and everything, all the atoms, all the air. Turn off all the electric and magnetic fields that might be pervading the room. Cool it down to absolute zero. What does it look like? It's just the vacuum. There's nothing, right? This is the vacuum. How can you study the vacuum? Well, I want to convince you, because it's important to have this concept in your mind, that this is not the right way to think about the vacuum in a quantum theory of reality. The classical vacuum, before, up to 100 years ago, when we thought classically, like Galileo and Newton, is empty, as pictured, and boring. But quantum mechanics, that can't be the case. So consider a pendulum, like in a clock. This is a pendulum at rest. That's very much like the vacuum. No energy, it's ground state, we say, no motion, boring. We can set it in motion, give it a kick, but that takes some energy and goes back and forth. That's an excited state, we would say. It's more interesting. But the lowest energy state, if we cool it down, is the state at rest, the ground state. That's like the vacuum. However, Heisenberg taught us in the beginnings of quantum mechanics that we have to be careful with such a picture, because the only way we could know that this oscillator is in its ground state is to observe it. Otherwise, who knows what state it's in? And if you observe it, you interfere with it, right? So how would we observe this pendulum? We would shine a laser beam on it, right? Like that, boom. And a little quanta of light would bounce back. We could see that it was in this state, but by doing so, we would give the oscillator, the pendulum, a little kick. So in quantum mechanics, we learned that every little oscillator has some, what we call 0 point, some inevitable lowest, no matter what you do, you can't get rid of it, because in order to observe it, you're going to set it a little bit in motion, some 0 point oscillation. This is related, of course, to the Heisenberg uncertainty principle. This kind of situation is impossible because you would know exactly where the oscillator is and what its velocity is, and that can't be the case in quantum mechanics. Because you observe it, you set it in motion. Now, this is true of every dynamical object in quantum mechanics. For example, a magnetic field and an electric field between charged particles is just a bunch of oscillators. Each one of them is fluctuating as this sort of quantum oscillation in the vacuum. So the vacuum can't be as boring as this. It has to be more like a collection of these oscillating oscillators in their lowest energy state, but still moving. And so I'm going to show you a picture, a calculated picture of what the vacuum looks like, full of fluctuating fields. And now, it turns out that the structure of the vacuum depends, again, on the scale at which you look at it. if you were really to evacuate this room of everything and look from the outside, inside, over macroscopic distances of a centimeter, it would look pretty boring. There would be no structure. But if you look with a powerful microscope, and in this picture, you're looking at a microscope whose size is about the size of the proton, then what you would see if you had instruments that could see, interact with, the chromodynamic fields that are holding the quarks together inside the proton, would be this picture of fluctuating quantum fields. Now, this is somewhat of an illustration, and this is the result of a calculation in quantum chromodynamics, the theory of the strong force, but that's a very well-tested theory, which we believe is true. So this is supposedly an illustration of what you would see, what the vacuum looks like if you could see the level of protons inside the atomic nucleus. This is not a boring state, right? This is like a lava lamp. This is a fluctuating, dynamical medium. Actually, it's very interesting. To make this kind of picture, you have to do all sorts of tricks, right? But if you understand the mathematics of these these are very beautiful and rich fluctuations. The vacuum is a very interesting object. You could stare at it for days. Especially around here. So what I want you to go away with is this is what the vacuum looks like. And quarks and nucleons and all the stuff you observe that we're made out of, all this stuff, are just ripples in this vacuum. And the properties of these quarks and the forces between them are greatly influenced by the medium in which they are immersed, which is this fascinating dynamical vacuum, which theorists like me and experimenters in effect have been probing for the last 50 years. And what we now want to probe down to much, much smaller scales. So I'm going to tell you a bit about how these forces work. So normally in these kind of talk, people just say, here are these forces. But I'm going to try to actually explain to you why they work the way they work. See if it works. First, we have the force of electricity and magnetism, and most of you, I'm sure, know something about electricity and magnetism. This is a force sometimes we feel. If you put your finger in the wrong place, you can feel this force. It's not very pleasant. It's a very powerful force, which is why you don't feel it most of the time. The only force we feel all the time is what? Gravity. Everybody feels. The reason we feel gravity is that there's no anti-gravity. There's nothing to shield. Everything is pulling on me, so I feel it. And the Earth is kind of big, so it pulls on me, and I feel it. But I don't feel the force of electromagnetism usually, even though we're all full of electrons, which have an electric charge and pull on protons. But what happens is they form atoms, and atoms are neutral. So atoms don't have much of a force between them. They have a very weak force, which gives rise to chemical bonds. That makes up ordinary matter. But at the basis of it all, it's electromagnetism, which is a theory, is the way we describe the force between charged particles. And electricity and magnetism is based on the first type of such theory of Maxwell, where we had one charge, the electric charge, the stuff that flows in wires, currents, is motion of that charge. Charges are held together in the atom. And as you probably know, two charges create a field which describes the force, which falls off like an inverse square law These are the lines of force or the lines of the electromagnetic field. Tells you what force there is on the charged particle at some point in space. Or we sometimes say that the quanta of that field mediates the force, the photon. Now, the force of electricity and magnetism is very simple. It's just this inverse square law, and it's been understood now for 160 years. And it isn't modified too much by the strange quantum vacuum. And that's why we didn't have to worry about the quantum nature of the vacuum until more recently. It gives rise to an energy, but not one that falls off like 1 over the distance. And that's why you can pull electrons out of atoms. There's something called the ionization energy. And if you have enough energy, you can pull an electron out of an atom. Which is very good, because then we can take those electrons and make them move in wires and go around wires and do work for us and create all modern technology. So that's electricity and magnetism. It's very simple. To understand the structure of the atom based on this force does require quantum mechanics. But that's another story. What about the weak nuclear force that acts inside the nucleus? Well, it turns out that in essence, at the heart of things, it's exactly the same kind of force as electricity and magnetism, except that now there are 2 charges. So we imagine 2 kinds of charge. Well, we have to call them something other than plus and minus, because there are 2 kinds of charges. And that's where this other name comes from, up and down quarks. The upness and the downness, if you want, are 2 of these weak nuclear charges. There's the up charge and the down charge. There's also an anti-up and an anti-down. The electron, or the positron, has the same charge as the up quark, and the neutrino the same charge as the down quark. And the force acting on these particles is kind of a generalization of E and M, except with 2 charges. Now, it's a little tricky. For example, to mediate that, you have now fields. But because there are 2 charges, there are more than 2 or 1 weak fields. In fact, there are 3. Now, how do you get 3 from 2? Well, the answer is you take 2 times 2 minus 1. If you have 3, as we will for the strong force, there will be 8. 3 times 3 minus 1. 8 gluons. And I will not try to explain to you this magic of non-abelian gauge theories, but one of the weird things that can happen when you have 2 charges is that now an up quark can turn spontaneously into a down quark and emitting a quanta of this weak field, which turns into a neutrino and a positron. This preserves the total charge. It's symmetric. But an up quark has turned to a down quark at the price of creating this other pair. This is the origin of the transmutation of elements. Because this up quark is actually inside one of the constituents of the proton. And when it turns into a down quark, the proton turns into a neutron. And it changes the atomic charge of the nucleus that it's bound to, emitting a positron and a neutrino. Or if you want, gold turns into platinum with this radioactivity, the transmutation of elements. This weak nuclear force, which acts on these weak charges, is which we call flavor. Charge we call flavor. Up, down, charm, strange, top, bottom, electron, neutrino, etc. are the two charges of the quarks and electrons, is what's responsible for radioactivity, the transportation of elements, and the ability to build up the elements we see around us, just starting from a universe which had in it just hydrogen and helium. Now, that's not the only new thing when you have these two charges, or you have the weak force. Something else is different, and that was known when people studied radioactivity in the 20th century, early on. This force acts only at very short distances inside the nucleus. Unlike electromagnetism, it doesn't act at large distances and fall off just like an inverse square law. And furthermore, it turns out that the force, the underlying theory, would have predicted that quarks and electrons would be massless particles, move like rays of light with the speed of light. And that certainly isn't the case. So to explain how that isn't the case for this generalization of Maxwell's EM, Higgs and others invented something called the Higgs mechanism, which is a way of modifying the vacuum in which these quarks and electrons live. And they did this by inventing a new object which would condense and exist throughout the vacuum, called the Higgs field. That was totally arbitrary, because nobody had ever seen it, but if you invented it, and then in a vacuum in which this Higgs field had condensed was full of this field, electrons and quarks moving around would be moving through sort of a molasses, and they would acquire a mass and would no longer be massless, moving with the speed of light. And not only that, but the field would become short-ranged. The carriers of the field would become massive, and it would look like a short-range force that only acted within the nucleus and would have massive quarks and electrons. It was just a theoretical construction to put together this idea of two charges and make it consistent with what we observed. It's by hand modifying the quantum vacuum. It worked. And the last prediction of this simple way of achieving that was a particle called the Higgs boson, which we now believe has been confirmed at the LHC. And I'll show you how this happened a year ago. So this, as you know, is this incredible construction of the human race. I mean, I regard this as the most amazing thing that humans have ever done. It's sort of in scale like the pyramids of Egypt, except, this is an unbelievable effort which took about 25 years, thousands of scientists and technicians, billions of euros to construct an accelerator that runs 20 kilometers around in France and Switzerland. This is the Geneva airport. Colliding protons at trillion electron volt energies in order to, among the rest, confirm this theoretical conjecture about the Higgs condensate and to discover new physics. It's an amazing accomplishment. It's an amazingly complex accelerator, amazingly complex particle detectors. This is the compact muon simulator. This is the Atlas detector. This is a person. These are toroidal magnetic magnets. The collision happens at an incredibly small point in the middle of this detector, and this unbelievably complex with millions of channels detector is necessary to to discover events like this. This is a reconstruction of what happens when the proton beams come together, spew out tons of particles, most of them uninteresting, and then two very intense gamma rays, or photons, and is the kind of thing that they were looking for to confirm the existence of this new particle. The Higgs, which should decay, should exist just for a brief moment and then disintegrate into two quanta of light moving off here. And by measuring the energies of these two photons, you can deduce the mass of this particle if it's there. Now, I want to show you how a discovery is made. So, you construct this accelerator, you construct this detector to see events like that. Oops. And we went too fast. To see events like this. What happens is, once every 10 or so nanoseconds, these bunches of protons that are going around at the speed of light almost collide, and a collision takes place. One in approximately every 10 billion collisions might look like this. Some of those events will be due to a particle, the Higgs, if it's there. Some of them will be due to other kinds of collisions, which we can predict to some extent using the standard theory. So what you're predicting is, oops, how do I go back? What you're predicting, what you saw was, what you saw was the prediction. So this is the prediction, and this is the amount of data you see here in numbers like 12 events, big error bars. This tests nothing. This is meaningless. Each of these points here agrees with the error bars with this prediction. There's no structure that is meaningful. Now you turn on the LHC, and instead of having 10 or 18 events, you have hundreds of thousands. And you will see the events, the error bars getting smaller, and a little peak coming out of the data around here, which at some point becoming a significant bump. And at that point, it becomes significant enough to say, okay, well, there's a real particle here, not this blue background, but a little bump. Those are the Higgs particles, and if the Higgs isn't there, this is very unlikely that we'll see something like this. There's another signal where the Higgs is supposed to appear and decay to 4 muons. A muon is a heavy electron-like object, lepton. These are very clean signals, no background, but there are fewer events, and this again is how, over time, this little bump emerges. And at some point, the experimenters say, well, this is significant enough, this red bump, for me to take courage and announce to the world we've made a discovery. And that's what they finally did. And by now, the evidence has gotten even stronger. At some point, they have to have enough confidence that this is not just a fluctuation but a discovery. So that was a major achievement and one of the last holes in the understanding of the strong, weak force, of the weak nuclear force. Now we come to my favorite force, the one we had something to do with explaining, the strong nuclear force, which has 3 charges. So everything we know now is 1, 2, 3, now 3. I told you there are quarks inside the nucleus, right? And it turns out that quarks come in 3 charges. So an up quark is actually, there isn't just one up quark. An up quark has 3 charges, extra charges. We could call them 1, 2, 3, or we could call them ABC, or we could call them red, white, and blue. And so here we use colors. A color is just, there are 3 colors, at least the American ones, red, white, and blue. And they're just names for the 3 kinds of nuclear charges. The up quarks have down quarks. Each of the 6 quarks we've discovered has 3 of these charges. And the force between these quarks is exactly the same, more or less, as electromagnetism. Here, too, an up quark and an anti-up quark have a chromodynamic field, which, if it weren't for the funny properties of the quantum vacuum, would look just like between electrons and positrons, fall off like 1 over r squared. You could pull the quarks out of the nucleus. Run them in wires, have quark wires and quark fields, chromodynamic fields. It would be kind of interesting. But it doesn't work that way. And if you take a quark and an anti-quark, try to pull them apart, the force doesn't fall off like 1 over the distance squared. It's different. And here the difference is, as we discovered, has to do with this properties of the medium, the vacuum into which the quarks are immersed. So the quarks sit in this vacuum, and this vacuum can't stand this chromodynamic field. In effect, it doesn't like it. It tries to squeeze it, to get rid of it. But it can't because the quarks are here. Now you could try to push the quarks together and they could annihilate. And actually that's what happens in reality if you don't hold the quarks in place. But inside the proton, there are actually 3 quarks and no antiquarks. And you can't get rid of them. You can't squeeze them away completely. So just like in this case where I hold the quarks down, the only way the vacuum can get rid of flux as much as it possibly can is to squeeze these lines into a tube, which is very small. A string, if you will. And that changes the law of force between the quarks. That is essentially the property we call asymptotic freedom. It explains that when the quarks are very close together, this phenomena doesn't happen really. In fact, the force gets weaker and weaker, but when you pull them apart, as flux lines are squeezed, the force is more like that of a rubber band than of an electromagnetic field. In fact, it doesn't fall off at all with distance. And if you were to try to separate, pull the quarks apart, the energy between them increases with increasing distance. And you can never actually get them separated. That we call quark confinement. And that explains why quarks can't be pulled out of the proton. You know, if you smash electrons together, electrons come flying out. Things get ionized, right? But the ionization of protons is infinite. That's why nobody's ever seen a quark. Quarks, the protons are neutral combinations of quarks. Now, I didn't explain to you how you can put 3 quarks together and make something neutral, but you can. And in fact, this is what happens to, well, that's what led us to understand the theory. But this again is a calculation within that theory of what happens. You pull quarks apart in this quantum vacuum, and you see that the formation of this tube where all the field lines are condensed. Very different than electricity and magnetism. We're actually made out of protons which have 3 quarks, and when you pull them apart, this is what happens to the field lines. You see, they all get squeezed as much as they can, and it would take an infinite amount of energy to pull a quark out of a proton. So nobody's ever seen a quark, yet they're there, and if you look inside, very short times, you see them moving around like free particles. These quarks are very light. They're almost massless. They get a teeny mass from the Higgs particle. But that's not what makes up your mass. One of the interesting things I like to tell people about the nuclear force is, so you're made out of these protons, which are in turn made out of these quarks. The quarks have no mass at all almost. Where does your weight come from? Where does your mass come from? Most people say, oh, my mass comes from the mass of the atoms. Where does the mass of the atoms come? It comes from the mass of the nucleus. Where does the mass of the nucleus come from? It comes from the mass of the protons and the neutrons. Where does the mass of the proton and neutrons come from? The mass of the quarks? No way. It comes from the energy of the quarks. Just the fact that that is confined energy. Einstein, E equals mc squared really is telling us that the energy of an object at rest is its mass. So it's the confined energy of these massless quarks, which are held together by these rubber bands that are rattling around with lots of kinetic energy, that sums up to give the mass of the proton and your weight. So it's kind of nice if you like that kind of picture, that you are just confined energy. And when you step on the scale and you see you've gained a kilogram, you think of that as another kilogram of confined energy. I'm not saying it, but it's really true. So even if, that people say the Higgs mechanism, Higgs particle explains mass. Well, it's true. It explains the mass of the quarks. But even if that hadn't been there and the quarks had been massless, the mass of the proton would have been maybe 1 or 2% different. Most of your mass is just confined energy. Well, that's the standard model, and I tried to explain to you it's as simple as 1, 2, 3, and all of these forces are inherently the same, but because of the properties of the vacuum, which is a very interesting place to live, they look different. And as I said in the beginning, physicists are never satisfied. If something works, they're unhappy because it doesn't give any clues as to what lies beyond the standard model, or answers some of the questions we still have. And we have many. And I'm not going to go into detail about what the questions are. Just, it is those questions that we don't understand within the standard model and beyond that, with Einstein's encouragement, prod us immediately to go on and look for new physics. Now that takes a bit of courage, because as Einstein said, the successful attempt to derive delicate laws of nature, I think he meant by delicate, he meant precise, along a purely mental path of a theoretical physicist, by following a belief in the unity of the structure of reality, encourages us to continue in that speculative direction, especially after you've been somewhat successful. But the dangers of which everyone must keep in sight who dares to follow it. And that's true. It's very dangerous to make assumptions or conjectures about the unknown. But that hasn't stopped us. And One of the things that was apparent after this new theory came into being and started to be tested and seemed to work, 1, 2, 3, was to try to unify all the different forces, electromagnetism, weak, strong, and the kinds of matter, see if they could fit together. After all, they're all, in essence, the same kind of force. The force is due to these charged particles with 1, 2, or 3 charges. Maybe you could fit them together into a theory of one kind of force with one kind of charge, well, or with, say, 5 or 6 charges that would combine all these different forces. And remarkably, all these pieces that were already known in the middle 70s fit together like pieces of a jigsaw puzzle, which was rather complete. As if there really was just one kind of force based on more charges, and one kind of matter which had more charges. In the simplest of these unification schemes, there would be 5 charges, which would be enough to explain all the quark and electron, neutrino, lepton charges, and we would contain all of those forces of the standard theory, and some more. But how could this possibly be? How could all of these forces look so different? Well, I sort of explained how that might happen. The vacuum could look different at different scales. And at our scale that we look, scales of atomic size, the vacuum could give rise, as it does for the weak force, to these, or the strong force, to these very different looking forces. If that was the case, we would expect that if we go to very short distances, where you can't see all that structure in the vacuum, which we could explore by going to very high energies, then we should see all the forces looking the same. They might look different on the scale at which there was that structure in the vacuum, but at very short distances you wouldn't notice that. And so, well, we can't do experiments that would push these forces out to very high energy or very short distance yet. This is where we now do experiments, maybe a little farther out. But even over these inner distances, you see the strong forces getting weaker at short distances, stronger at large distances. Electromagnetism, the opposite. So what happens if you extrapolate? Well, it was already discovered in the 70s that you extrapolate, they come together. At very high energies, this is theorists extrapolating, pencil and paper, on paper, not building a better accelerator. If they build a better accelerator, this extrapolation would say you would see the unification happen in front of you. At least the forces which naturally look alike, but also be of equal strength at this distance. And you can understand the properties of the quantum vacuum which would make them look different at scales we observe today. Well, that's an extrapolation. So you speculate that there's unification at this scale. Remarkably, this is the scale where gravity becomes a strong force. You might think that gravity is the strongest force in the universe, right? Because you feel it. But that's only because it's the weakest force, and it can't be shielded. But you see, if you want to convince yourself that gravity is very weak, all you have to do is hold something up in the air by exerting a little bit of chemical, electromagnetic, the origin of the energy you use in your muscles, the forces you can exert, is electromagnetic. So I'm exerting a little bit of electromagnetic force, and the whole Earth is pulling down, and a little bit of electric force is holding this up against the whole Earth is going to go down coherently. Every atom in the Earth is pulling on it. Gravity is a very weak force. But gravity is very similar in a basic sense to these other forces. It too is a force between charges. The charges are, not in this case, the energies of the particles, or their masses. Gravity acts on mass. Mass is energy. So if you go to high energies, it gets much stronger, like energy squared. And at this scale of unification, it becomes equally strong. So maybe all the forces unite at this point. Now this is a typical situation that we all face as theoretical physicists. This kind of extrapolation and phenomena is either a very important clue for unification of all the forces with gravity at these very, very small distances, or energy, very high energies, or it's just a coincidence. Could be. There's no logical way to decide. This is where intuition, or your speculation, or your guesses are made. By and large, that my colleagues and I many have followed this as a very important clue for unification of all the forces with gravity at these very short distances. Now, this is actually a little depressing because these distances here, these energies, are so extraordinarily big that we can't imagine doing experiments here. And we can't even imagine how they would be done in 100 years from now. But who knows? But meanwhile, we can't directly probe this scale, so we have to probe it indirectly. And it could be just a coincidence. We don't know. That's the wonder and the excitement of exploring of fundamental science, which is always having to follow such clues, which might be just coincidences. Luckily, there are things at low energies, at larger distances, right around the corner, that follow sometimes from speculations about what goes on up here, or from other reasoning. And one of them, which we're still waiting for, have been looking for the last few years at the LHC, and still haven't found, but some of us still think could be there, and we will know shortly, is something called supersymmetry, that I don't have time to explain to you, but it's kind of a indication that there would be quantum dimensions of space and time. It's a fascinating symmetry of an extension of space and time to quantum dimensions. And again, we have a whole bunch of clues as to the possible existence of this extension of our customary understanding of space-time. The clues partly have to do with this unification. This is actually a way of picturing how those forces come together, which is a little more precise. These are the inverse of the forces. 3 lines, which is a function of energy on the logarithmic scale, are straight lines, which should meet in a point. And in the standard model, after 20 years of much more precise measurements and calculations, they don't exactly meet, but if you go to these supersymmetric worlds with quantum dimensions, they do. And that again could be an important clue that there is unification and this new quantum dimensions and supersymmetry, or it just could be a kind of coincidence. There's the astronomer's observation that most of the matter in galaxies and in clusters of galaxies is not made out of normal matter that we're made out of, protons and nucleons and baryons, but something they call dark matter, which they think is made up of very massive, weakly interacting particles, WIMPs, but nobody knows what WIMPs are. Nobody's seen them, nobody's produced them. One of the biggest challenges for us. And supersymmetric models predict, naturally, a candidate for this dark matter. Again, an important clue for supersymmetry around the corner. Dark matter would be some of the new particles that supersymmetry predicts, or a coincidence. So we have these clues, these speculations, these predictions, and we wait for the LHC to produce events that look like this, where you see collision is taking place here, lots of energy, a lot is going out in this jet of particles, jet 1, jet 2, but it's all going upwards, so there must be something going on here, and such an event would be a missing energy event. Maybe this particle of dark matter predicted by supersymmetry that you can't see, but whose properties you can deduce by its absence. By the fact that something had to carry this amount of energy and momentum, and you can thereby deduce its properties. And this is what people have been looking for the last 2 years, and will look for when the LHC turns on again in 2 years, with twice the energy and more events. If they discover it, I just want you to understand that this will be discovering quantum dimensions of space and time. And that would be a really big revolution. It would mean that, at the very least, we're not living in space and time the way we normally think about it, the 3 dimensions, They're extra dimensions, except they're even weirder than just the kind of extra dimensions I'll be describing in a moment. These are quantum dimensions. And this is something we could discover or rule out to some extent in the next few years. But I want to get on to more of these things quickly. And here we take seriously this clue that gravity becomes important. Because that forces us to understand strong gravity, quantum gravity. And that's what essentially led us to string theory, which is really the only successful attempt to do this. You see, gravity is a very complicated force, as Einstein explained, because it essentially arises from the dynamics of space-time itself. And most people's picture of space-time is as, well, space-time is something we live in. It's just out there, we live in space. It's not a dynamical thing. It's just a coordinate system. But Einstein explained that the metric of space-time, the thing that determines the distances between points in space and in time, is a dynamical object, a field, like the electric field or the chromodynamic field, and it is dynamical and changes, is affected by mass, by energy, curves, and its effect then on the motion of particles is what we call gravity. So what he explained was that the curvature of space-time caused by energy or matter gives rise to the motion that we call gravity. The gravitational force is a consequence of the dynamics of space-time. In quantum mechanics, however, everything is always oscillating, so that means that space and even time is not just some kind of fixed way of describing events, but is a dynamical object itself. And that's all right as long as those fluctuations that we describe are small. But when they get to be violent, it's hard even to apply our normal conceptions of space and time when things begin to get bad. And so that's one of the reasons it's been so hard to incorporate gravity together with quantum mechanics until we were led to string theory. Now, originally string theory arose as an attempt to understand actually quarks, the strong nuclear force, which isn't surprising because, remember, there's quarks, when you pull them apart, have this very flux tube between them, which looks like a fat string. So the original development of string theory was an attempt to understand, if you want, these flux tubes. Later, it was discovered, in this theory as it was being developed, that those strings, which could be closed, an open string could be tied together and form a closed string, and that when you worked out the properties of closed strings, they looked like gravity. They looked like they were the origin of the gravitational force. So from the beginnings of string theory, one reinterpreted as it was later as a unified theory, you had both gravity and the kinds of objects that we have in the standard model. Now, string theory has now been around for 45 years. It's kind of amazing. 45 years? And originally the hope was that this theory, which described both gravity and the kinds of particles we have in the standard model, could provide us with an explicit so-called theory of everything, or unified theory of all forces, and help us answer many of the why questions about the standard model. Why are there these three forces? Why are there three families of quarks and leptons? Why do they have the masses they do, et cetera, et cetera, et cetera? And to some extent it has. It has provided us with a theory of quantum gravity, which works very well and enables us to explore some of its strange quantum properties. And it has supplied examples of how all the forces can be unified. And it has unified in this way of open and closed strings, as we understand now in a much deeper fashion, are theories of the standard model with theories of gravity or closed strings. It has also raised many new questions. Again, making progress raises new questions, new ignorance. For example, from the beginning, string theory required that the number of ordinary spatial dimensions be larger than 3. That one, and that one. That contradicts ordinary experience. But not necessarily. How do you know that there are only 3 dimensions? If there are only 3 dimensions and you fix this direction, that direction to be this point, and you look at this point here with a very good microscope, you see nothing, you just see a point. String theory, however, the possibility is that there are extra dimensions at each point, little curled up dimensions that you just can't see because you can't resolve distances that are this small. And in fact, you can determine the geometry of these extra dimensions that are allowed in string theory by solving equations, generalizations of Einstein's equations for the dynamics of space that determine the geometry of these extra dimensions. So, you can imagine, indeed, that at each point in space, there are these little, beautiful little curled up manifolds. And there are many possibilities, it turns out. The beginning was awfully exciting that we could find 1 or 2 possibilities that looked a lot like the real world. Now there's zillions. Each one of these possibilities, the nature of the forces that we observe at distances which are big compared to the size of these internal manifolds, are, what kind of matter you have, or what kind of forces, and the values of the masses. Questions that the standard model cannot predict as to input from experiment and measurement are determined by the shape of the hidden dimensions. That is an absolutely beautiful way of answering the question that in the standard model, we have no way of answering. And to reduce the answer to geometry is an accomplishment that the Greeks would have loved. The problem is, however, that there isn't just one of these solutions. There's zillions and zillions of people discover more and more methods of constructing such solutions every week. And no principle for picking out which of them is supposed to be described by the real world. In fact, some ways they all seem problematic. But even if the problems aren't real or avoidable, there's just too many. That has given rise to these speculations and fantasies about the multiverse. But it is a problem, a failure of this normal approach that theorists follow. You make some bold speculation. You check whether it makes sense mathematically. You check whether it makes sense physically. You check whether it reduces when the parameters are correct to this incredibly successful theory you already have, so it's consistent with experiment. And then you try to make predictions or use the power of this new theory. Well, we can do that, except there are too many solutions. And it seems hopeless. Something is missing. One of the things that's clearly missing is we're not sure what this string theory is, actually. I showed you what the standard theory was. I wrote it down on one t-shirt, right? One slide, the equations. I can't do that for string theory. Nobody can. You ask a string theorist, well, what are you working on? I'm working on this or that part of string theory. But you ask them, what is string theory? In the end, they'll have to admit they don't know. So we're sort of, in the beginning, we believed this theory was, there was the standard framework we had after quantum mechanics that has been used to describe the standard model that I talked about. And then there was this new idea that instead of particles, we had extended objects, and all the particles we've ever discovered are just different modes of vibration of one extended object. And now we discovered that these sometimes are just different ways of describing exactly the same physics. But these aren't really different frameworks, they're identical. And I believe that, in fact, that's the case. String theory isn't as revolutionary as it seems. It's just that in certain cases we want to describe quantum gravity and so on, certain cases the right way to describe things is in terms of strings. In other cases, quantum fields. String theory and quantum field theory aren't theories either, they're frameworks. The standard model, which is a theory, is a specific example of a quantum field theory. Probably also has, we believe, a description as a string theory. But it is very specific. It has these special forces with 1, 2, or 3 charges. And we don't know why that is, but that's what makes it a theory that allows us to calculate. And in this bigger framework, we don't know what the principle is that picks out the theory that describes quantum gravity and the physics we observe around us. What's missing is something that picks out the actual dynamics we observe. The particular solution, so-called of string theory, that we would like to compare with the experiment. So in my opinion, we're missing something. We're missing a new principle based on, who knows, some of the old principles we've used often to pick out a particular theory, perhaps a new one. And there are plenty of places to look why we would need a new principle in our understanding, but we need something that will pick out a unique solution, a unique universe out of, if you want, this multiverse that seems to be described by this incredibly broad framework that string theory has led us to. What fixes the dynamics? What fixes the state of the universe? Now, one of the things we have to face for the first time in the history of physics is this question here. What fixes the initial state? See, physics is the game of predicting the future if you know the present. That's what we do when we test our ideas experimentally. We set up an experiment. We set up an initial condition. Then we use the laws of physics to predict the future and make predictions, and the experimenters go out and do a measurement in the future and test those predictions. But now we have to discuss the whole universe. You see, the space-time itself is dynamical. We know a lot about the history of this dynamical object we live in called space-time. We know sort of that it began with the Big Bang, but we don't know what the Big Bang is. And we are now faced with a situation where the goal of fundamental physics is to describe space-time. Now, it's even worse than that, if that's possible, because when in string theory we start looking at space-time, many of the properties of space that we are accustomed to disappear. For example, space is the smooth thing we live in, the smooth manifold, mathematicians would say. But that need not be the case in string theory at all. Spaces we live in have a fixed topology. They don't have holes. You can't go around like a torus, a donut. The topology is fixed. In mathematics that we use to describe physics, if you change the topology, awful things happen, but in string theory sometimes that doesn't happen. You can continuously change the topology. We usually think there might be extra dimensions, but the number of dimensions is fixed. It turns out that in string theory, you can, in effect, by changing the parameters or the physical system you're looking at, change, in effect, the number of dimensions of space. So space doesn't even have to have a fixed number of dimensions in a real sense. In fact, we believe more and more that space-time itself is probably best viewed as an emergent concept. And of course that means that gravity is emergent in the same sense, because gravity is the dynamics of space and time. Now, this is very difficult to totally comprehend, and we're far from comprehending it. But we seem to be challenged to regard to space and time our most fundamental concept of physical reality once again seems to be challenged, as it was 100 years ago by Einstein in his theory of special and then general relativity. But now it's even worse. You have to remember that space and time is something that each of us constructs as infants. Infants are born with very few concepts of physical reality. They have a built-in ability to assimilate sensory information and construct a model of reality. At the same time, they're constructing their brain that is supposed to comprehend that reality. One of the first things they construct is a model of space and time so that they can function. Like get from here to there, get the toy. You have to have a model of space. But remember, space isn't something that has as much of an obvious existence as the table you can touch. It's really something you construct in order to place events and construct a picture, successful picture of reality. So it might be just an approximate way of describing reality. That's what one really means by emergent. There might be a better description that is more accurate, true to the truth, and more powerful than space-time. Much as it's only an approximation to say that this table is a hard, continuous object, it's actually, we know, a better description is mostly vacuum with very small nuclei which are held in a periodic structure and electron clouds around them. That is a much better picture of the table, but from that I can understand how this other picture emerges of a solid object. This raises immense conceptual problems. If there is an underlying description of physical reality that for which space and time are emergent quantities, can we imagine then physics with more than one time? How do we set up physics without time, without space and time? What does it mean to predict if time is an emergent quantity, etc.? And finally, what does it mean to describe the beginning of space and time, the Big Bang? And this is a question that is not only important for fundamental physics, understand the answer to quantum gravity or unification, but for astronomers and astrophysicists who now try to understand the quantum fluctuations close to the Big Bang that end up being these ripples in the cosmic microwave background that eventually become planets and galaxies, and the structure that emerges here. So, the beginning of the universe, the nature of the Big Bang, is now a question of enormous interest, and it is related to this question I asked, how did the universe begin? Can we determine the beginning, the initial condition? Again, this is a question physics has never had to answer. We can't avoid it anymore because we're told that the universe is this space-time history, the beginning and the end. And if we're going to answer the question, what picks the dynamics? What picks the solution in this framework that includes string theory and everything? We're going to have to answer this question, including the beginning and the end. And here, we're in a very unusual state where we are sometimes in physics where we don't even know what the rules are. We've never had to answer a question like this. Very shaky grounds. That usually means that something is flawed with our basic conceptual frame. Something is wrong with the way we ask the question. And if we knew enough to ask the question correctly, we might be able to answer it, but we don't even know what the rules are. So, to conclude, we have a wonderful theory, elementary particle, standard theory, 1, 2, 3, and even more amazing set of questions to answer. Unification, the nature of space-time, the beginning of the universe. We have fantastic instruments that have, so far, once again verified with exquisite precision this incredibly powerful theory, but are set to make, we hope, real some of our speculations, and in my opinion, the best is yet to come.